Now we're going to talk about quadrature, that is the numerical approximation of definite integrals. In theory, any method that we have for approximating f, if we can integrate the approximate, could be used to approximate the integral of f. For example, we could fit a cubic spline to f and integrate the cubic spline, and in fact that's done. It's particularly useful when all you know about f are its values at certain points. We could use a high degree polynomial that interpolates at a lot of points, but we know that high degree polynomial approximation can give very bad results in some cases. So what we're going to do is approximate f by piecewise Lagrange polynomials. That is, we're going to divide the interval a to b up into n strips. For the moment, we'll assume they're constant width strips, width of h, but they don't have to be constant. And the problem basically boils down to approximating the integral of f over one of these small strips from xi minus 1 to xi. For example, Simpson's rule is based on approximating f by a polynomial of degree 2, which interpolates to f at 3 points in each strip, the left-hand point, the right-hand point, and the midpoint. And it's easier to derive if we assume that our little interval goes from 0 to h rather than xi minus 1 to xi, and then once we derive it, we'll just move everything back to the real interval xi minus 1 to xi. So you can approximate f on the interval 0 to h by the Lagrange polynomial of degree 2, which interpolates to f at 0, the midpoint h over 2, and the right-hand point h. And here is the Lagrange polynomial. This will be familiar. So we simply integrate this Lagrange polynomial of degree 2. The f of 0 is a constant. It comes out, and you just have to integrate this. The f of h over 2 comes out, and you integrate that, and here's the results. You get h over 6 times f of 0 plus 4h over 6 times f at the midpoint plus h over 6 f at the right-hand point. So that's Simpson's local rule on the interval 0 to h. If we want to use it over the interval a to b, we divide a to b into a bunch of strips, and in each one we approximate the integral over that strip by h over 6 times f at the left-hand point plus 4h over 6 times f at the midpoint plus h over 6 times f at the right-hand point. This is called the composite rule. That's the sum of the local rules, sometimes called the global rule. In general, if we decide we want sample points R1, R2, and R3, then the quadrature rule would be the sum I equals 1 to n of W1H times f at xi minus 1 plus R1H, etc. The R's are called the sample points, the W's are called the weights. And we could derive any of these rules once we've decided what sample points to use. For example, Simpson's rule, we decided we wanted to use 0, 1/2, and 1. Once we decided which sample points to use, we could simply write the Lagrange polynomial like we did here and integrate it and find the weights. And in fact, we can do that if we want just 2 sample points with sample points of 0 and 1. In other words, the left end point and the right end point. That's called the trapezoid rule, and the weights turn out to be 1/2 each. Simpson's rule, we just saw that. If you want to use a polynomial of degree 3, which interpolates at 0, 1/3, 2/3, and 1, that is 1/3 of the way across the interval, 2/3, and all the way, then the weights turn out to be 1, 3/8, 3/8, 1/8. If you want 5 sample points at the left-hand point, 1/4 of the way across, 1/2 of the way across, 3/4, and all the way across, the weights turn out to be that. Again, that you can get by writing out the polynomial of degree 4, which interpolates to f at these points and integrating it. And of course, you can keep going. These are called the Newton-Cotes formulas. They're based on uniformly spaced points. We've a priori decided we wanted to use uniformly spaced points in all of these, and we write out the Lagrange polynomial that interpolates to f at those points, integrate it, and we get the weights. If we want to get theoretical error bounds on these formulas, we could simply include the Lagrange error term and integrate it and get a bound on the error for each of these. But there's actually a simpler way of getting an error bound, which comes from the following theorem. And this theorem is very useful. It can not only be used to find an error bound on a quadrature rule that you've already derived, but it can be used, it's probably the easiest way, in fact, to actually derive quadrature rules. It simply says that if a quadrature rule is exact for 1x squared up through x to the m, in other words, exact for all polynomials of degree m, then the global error is bounded by a constant, depends only on m, by the maximum of the m plus first derivative of f times h to the m plus 1 power. In other words, if a quadrature rule is exact for all polynomials of degree m, its order h to the m plus 1. Notice that again we see that polynomials have a special place in numerical analysis. A similar theorem does not exist for other types of functions, only polynomials. So basically polynomials are the guinea pigs if you want to know how well your quadrature rule will do on general smooth functions. Try it out on polynomials, try to make it exact for as high degree polynomial as possible. That's what this theorem says. The proof of the theorem, we define the local error to be the integral of f over the little strip minus the quadrature rule's approximate. This is the approximation of that integral. So this is the local error. Then we write f as a Taylor polynomial of degree m plus the remainder term, where Tm is the Taylor polynomial of degree n interpolating at, say, the midpoint of the interval, and R of m is the Taylor polynomial remainder. Well, remember that the remainder term for Taylor polynomial is x minus x mid, since x mid is the point of interpolation, to the m plus 1 power over m plus 1 factorial times the m plus first derivative of f at some point between x and x mid. Thus, in the interval xi minus 1 to xi, there's a bound on the remainder term of h over 2 to the m plus 1, because x can never be more than h over 2 from the midpoint, over m plus 1 factorial times the maximum of the m plus first derivative of x in the whole interval. Now notice that the local error in f, by linearity of the definition of E, is equal to the local error of the Taylor polynomial plus the local error of the remainder term. But by assumption, the quadrature rule is exact for all polynomials of degree m, therefore the local error for Tm is 0. So all we have left is the local error of Rm, which is going to be small. Rm itself is small. And by definition, the local error in Rm is this. There's the integral, local integral. Here's the local approximation. And everything's small here. The integral can't be more than h times the maximum value of Rm. And Rm at each of these points is less than whatever its maximum value is. So take out the maximum value of Rm, absolute value of Rm, and you got h from this integral, h times absolute value of W1 from the first term, and so forth. And now using the previously determined error bound on R, or bound on R, we have the following. Rm is less than h to the m plus 1 over 2 to the m plus 1 over m plus 1 factorial. Then so we got this extra h from here. Rm is less than h to the m plus 1, so that gives us h to the m plus 2 power here times some constant that depends only on m. By the way, the weights will normally be positive, and they'll always add up to 1, so normally this big term in parentheses is just going to be 2 unless some of the weights are negative. In any case, it'll be some constant. So we have local error is less than h to the m plus 2, and the global error is less than n times the largest local error, but n contains 1 over h in it, so you lose 1 power. So the global error will have h to the m plus 1 power. The local error is always one order higher than the global error, because the global error is n times the local error, and n is proportional to 1 over h. So for example, Simpson's rule, well, it turns out that Simpson's rule is exact for polynomials of degree 3, so the global error is h to the 4th. Actually, the local error for Simpson's rule is h to the 5th. Going back to the Newton-Cotes formulas, the ones based on uniformly spaced sample points, the trapezoid rule was derived by approximating f by a polynomial of degree 1, so it's obviously going to be exact for all polynomials of degree 1 and therefore be global order h square. Simpson's rule was derived by approximating f by a polynomial of degree 2, so certainly it will be exact for all polynomials of degree 2. You interpolate to a polynomial of degree 2 by a polynomial of degree 2, you're going to get exactness, 0 error. So it's going to be exact for all polynomials of degree 2 and therefore order h cubed. But actually Simpson's rule gets lucky. By symmetry, it's actually exact for all polynomials of degree 3, so it's really order h to the 4th. So the Newton-Cotes formulas that are based on interpolation by a polynomial of degree k are going to be exact for polynomials of degree k at least, sometimes one more than that, and therefore they'll be order h to the k plus 1. However, the Newton-Cotes formulas are not widely used except for a trapezoid in Simpson's rule, because we can do better than Newton-Cotes formulas. These are all based on a priori deciding that we want uniformly spaced sample points, and we say what are the best weights given those sample points. And by the way, you can derive these methods. In fact, it's simpler to derive them by using the theorem and simply adjusting the weights until the formula is exact for as high a degree polynomial as possible. But we can do better than the Newton-Cotes formulas, because once we decide that we want the sample points to be uniformly spaced, see, it only gives us, well, let's say, for example, the 3-point Newton-Cotes formula, Simpson's rule. Once we've decided we want the weights to be at 0, 1/2, and 1, that only leaves us 3 parameters, the 3 weights to play with. So you would expect to only be able to make it exact for 3 functions, 1x and x squared, and therefore it would be order h cubed. Actually, it turns out to get lucky and be order h to the 4th, but you only have 3 parameters. Gaussian quadrature, the idea behind Gaussian quadrature is to say maybe those uniformly spaced sample points aren't the best. Let's keep an open mind about the sample points and let those be variable also. And then we have 6 parameters, the Gauss 3-point formula, that is. Once we decide we want to use 3 sample points and 3 weights in each interval, then that gives us 6 parameters to play with, the 3 weights and the 3 sample points. Therefore, we have reason to hope that we might be able to make it exact for 6 functions, 1x, x squared, x cubed, x to the 4th, and x to the 5th, and therefore be order h to the 6th. And in fact, that's exactly what we're going to do. So the Gaussian quadrature formulas are optimal. That is, they used not just the best weights for given sample points, but the best weights and sample points. And there's actually a Gauss quadrature formula for every n, for every number of sample points per interval you want. There's a Gauss 2-point, 3-point, 4-point, and on up forever. We're going to look at the Gauss 3-point quadrature formula. That means that we approximate the integral of f over each strip using 3 weights, 3 sample points. We have therefore 6 parameters, and we can hope to make it exact for 1x, x squared, x cubed, x to the 4th, x to the 5th. At least if we plug this formula n with f equal to 1, x squared up through x to the fifth, we will have a system of 6 equations and 6 unknowns. They're nonlinear equations, so it'll be very difficult to solve, but usually linear or nonlinear, a system of 6 equations, 6 unknowns has at least a good chance of having solutions, and it does. However, actually solving those 6 equations, nonlinear equations, is very difficult. So what we're going to do is make things simpler, and let's assume we're only going to use one strip. So n is 1, and we're going to integrate from -1 to 1. So we'll take a to be -1, b to be 1, and only one strip. That means h is b minus a is 2. So we plug in h equal to 2 here. The left-hand point, there's only one, there's no sum, there's only I equals to 1 only. And the left-hand point is -1. So replacing h by 2 everywhere and xi minus 1, which is a, which is -1, we get this formula. And so we're basically trying to derive the Gauss 3-point quadrature formula on the interval -1 to 1, simply because the algebra will be much simpler. And this is, in fact, where all the Gauss quadrature formulas are derived for the same reasons. So now we want to find weights and sample points which make this exact for as high degree polynomial as possible. Well, converting to the interval -1 to 1 makes things simpler. If it's exact on one strip, it's exact on the sum of all the strips, so we can just look at one strip and we can make that strip be -1 to 1, as I said. Now if we plug in f equal to 1, x squared up through x to the fifth, we will indeed get 6 equations, 6 unknowns, but it's still going to be a big mess. So to make things simpler, we're going to think about it a minute and say we're integrating, we want the best possible weights and sample points on the interval -1 and 1 for general f. Surely they will be symmetric. In other words, the 3 points are bound to be, one of them will be right in the middle and the other 2 will be opposites. There's no reason why the sample points should not be symmetric around the middle, the optimal sample points, not for a particular f but for general f. So we're going to assume that the sample points -1 plus 2 Ri are going to be -s, 0, and s. And once we've assumed that the sample points are symmetric around the middle point 0, there's no reason why the first and last weights won't be the same. They don't need to be the same as the middle one. So we're going to assume that our quadrature rule has the form a f of -s plus b f of 0 plus a f of s. In other words, assume that the first and last have the same weights and their opposite sample points, and the middle one is right in the middle. Now you might say, well, now you only have 3 parameters left to play with, so you'll only be able to make it exact for 1, x, and x squared. It's not true. We haven't really thrown away any parameters. We just used a little common sense and said the optimal parameters are surely going to be symmetric. So, you know, if you don't believe that, you can not assume symmetry and solve the 6 equations. You'll find they are symmetric. So we're going to simply take advantage of symmetry to decrease the number of parameters. And here we go. We're going to plug in f equal to 1, x squared, x cubed, and so forth. So we assume f is just the function 1 and x squared, so forth. And the right-hand side we get, when f is 1, then f of anything is 1, so that's just a plus b plus a. When f is x, f of -s is -s, f of 0 is 0, f of s is s, and so forth. F of x is x squared. This would be a times -s squared plus b 0 squared plus as squared, and so forth. Now notice the odd powers all, the integrals of the odd powers are all 0, because you integrate an odd power and you get an even power, and plug in the upper and lower limits, they cancel. So the odd powers 1, 3, and 5, all the integrals are 0, and by symmetry the approximation is also 0, no matter what a, s, and b are. So we see, we get these 3 equations satisfied for free by the symmetry, because the odd powers, the -s and the +s, cancel, and the b is multiplied by 0. So for x, x cubed, and x to the fifth, those are satisfied for any a, b, and s. So we basically have only three equations for our three unknowns, these three, the even powers. And there are our three nonlinear equations for our three unknowns. In this form, they're not that difficult to solve. You can simply take this divided by that. That gives you s squared. This over that gives you 3/5, so s squared is 3/5, so s is the square root of 3/5. Then you go back and solve for a, it's 5/9, b equals 8/9. So there's the weights and sample points for the interval -1 to 1, but now our r's and w's, which we need to actually program this method, those are the weights that we use in a real strip, xi minus 1 to xi. You have to go back and remember the conversion from the r's and the w's to the s's and b's. R1 will be 1 plus s over 2. R2 is just going to be 1/2 right in the middle. R3 will be 1 plus s over 2, and so forth. So we get these values for the sample points, and the weights are just half of the a, b, and a. So 5/8, 8/18, 5/18, 8/18, and 5/18. So in fact, we were able to solve the 6 equations and 6 unknowns. We have found weights and sample points, which will make our 3-point formula exact for polynomials of degree 5, which means it should be order h to the 6th, which is much better than Simpson's rule, which is order h to the 4th. Actually, it got lucky. Normally, the Newton-Cotes 3-point formula you'd expect to be order h cubed. For any number of points, for example, if you want a Gauss 10-point formula, you end up solving a system of 20 equations and 20 unknowns. There will be a solution. All of the sample points are between 0 and 1. The weights are all positive. Everything's great. So for any n, there is a Gauss n-point formula that's order h to the 2n. And in fact, an interesting fact about Gaussian quadrature is you could actually fix h and let the number of points go to infinity and it will still converge. With Newton-Cotes, that's not the case. If you fix h, maybe make just one strip, say, and use a trapezoid rule, then Simpson's rule, and then Boole's rule, and then keep going higher up, higher and higher order, there's actually no guarantee that that's going to converge. We know that polynomial approximation with uniformly spaced points can be actually very bad. So even for nice smooth functions, sometimes that using higher and higher Newton-Cotes formulas with a constant h will not converge. Surprisingly, it will converge for Gauss quadrature. For any even just continuous function, if you take higher and higher Gauss quadrature rules, keeping h fixed, it will actually converge, and generally converge quite fast, although hardly anybody actually does that. Normally you fix the number of points per strip, and if you want more accuracy, you just make h smaller, and because it's a lot simpler, if you want to use arbitrarily high Gaussian quadrature rules, you've got to calculate the coefficients for a lot of points. Okay, we're going to do some get some experimental results with our Gauss 3-point formula in a moment, but let's talk about the experimental order of convergence. When we talked about root finders, we defined order to be something entirely different. There, the error on a given iteration is proportional to the error on the previous iteration of the alpha power. We said that alpha was the order. Here, order means something different. It's the power of h that the error is proportional to. So, for example, we've already seen that a method that's exact for polynomials degree m is theoretically order m plus 1, h to the m plus 1. But we can have an experimental order of convergence, just like we had experimental order of convergence for root finders. And if you know the exact integral I, then you can calculate the error for each h. And to calculate the order, you simply make 2 runs with 2 different values of h. Let's say you do it with h and then cut the step size in half. That is twice as many steps. Half is small. then E of h is assumed to be approximately m times h to the alpha. If you cut h to h over 2, then the error should be approximately m times h over 2 to the alpha. You simply take the ratio of those two runs. That gives you 2 to the alpha, and then you can solve for alpha. It's the log of the ratio divided by log of 2. So, for example, if Simpson's rule should be order h to the 4th, so you would expect that every time you cut h by a factor of 2, the error should go down by a factor of 2 to the 4th, or 16. So once you know the ratio, you can find the order. Now, sometimes you don't know the exact integral, so you don't know I. Then you can still calculate an experimental order of convergence, but now you have to do 3 experiments, because now, see, before, if you knew the exact integral, you didn't know m or alpha, so you need 2 experiments to find m and alpha. We're not really interested in m, just alpha, but we could find m also. If you don't know I, then there are actually 3 unknowns, I, m, and alpha. So you need to run 3 experiments. Remember, these i's here are known. Those are your experimental integrals. And the h's are, of course, known also. So we're trying to solve for I, m, and alpha. And here's how you can do it, assuming you cut the step size by 2 each time. So you make 3 runs, each one cutting this previous step size by a factor of 2. How can we solve this for alpha? Well, we subtract the first equation minus the second to get rid of the I, and we get that. Then we take the second equation minus the third to get rid of the I there, and we have that. And now you see we've got it down to 2 equations for 2 unknowns, m and alpha, and we can simply take the ratio. Everything on the left-hand side is known here. We can simply take the ratio to get rid of the m, and that comes out to be 2 to the alpha again. So here's the ratio you can calculate if you don't know the true integral. You have to do 3 runs, and again, if it's a 4th degree, 4th order method, you should get a ratio of about 16. You can calculate the experimental order as the log of this ratio over 2. So if you know the exact integral, you can simply make 2 runs and get the ratio. How much does the error go down there? If you don't know the integral, you have to make 3 runs and take the ratio of the difference between the first 2 and the difference in the second 2. Okay, let's do a little MATLAB test here. I've written a Gauss 3-point program. Looks like this. You pass it the endpoints and the number of strips you want, and the weights and the sample points are calculated exactly using the formulas we've given, and then you add up over each strip the first weight times the function at the first sample point plus second weight, second sample point, and so forth. So this is exactly as we discussed it. Sum over I equals 1 to n. This is actually xi minus 1 plus r1h, xi minus 1 plus r2h, r3h, and the weights are w1, w2, w3 times h. So here's our Gauss program. We're going to test it on the square root functions. Our function is simply the square root of x, and we're going to integrate between 1 and 4. So we're going to call our Gauss 3 routine and integrate the square root from 1 to 4. We'll do it with n equal to 10, 20, and 40, so h is being cut by a factor of 2 each time. The true integral of square root of x from 1 to 4 is 14/3, so we can calculate that first ratio, the error on the second test divided by the error on the third test, and calculate an order that way. If we didn't know the true value, we could still calculate the order using the other formula, so we're going to do both. And remember that in theory, the Gauss 3-point formula is 6th order. And in fact, the ratios in both the test using the true value and the test not knowing the true value both come out to be reasonably close to 2 to the 6th power, 64, so the orders both come out to be close to 6, exactly as we would expect. Now let's go back and make another test. This time, let's integrate the square root function from 0 to 1. Now the true integral is 2/3. And now, very surprising, the ratio in both cases is nowhere near 64, and the order is nowhere near 6. In fact, it's 1.5. So the experimental order is much smaller than expected. Why? The answer to that question can be found by going back to the theorem on which the order is based. Our Gauss 3-point formula, remember, is exact for polynomials of degree 5. Therefore, the error is bounded by h to the 6th power. However, there's the 6th derivative of f in front of it, the maximum 6th derivative. Well, on the interval, the 6th derivative of the square root function is something times x to the minus 5.5 power. So it has an x to the 5.5 in the denominator. And between 1 and 4, that's no problem. It works just fine. But if the interval is 0 to 1, you see the maximum of this is infinite, because x can be as small as 0. Well, it's much like the analysis of the Newton's method for the root finder. It's normally second order, but the constant out front is infinite. All bets are off. That's what's happening here. It's 6th order, but the constant out front is infinite. The maximum of the 6th derivative is infinite. Then it's not really 6th order. In fact, it turns out to be, as we just saw, about 1.5th order. It still converges, but much slower. Well, what can you do about that? You could simply make the strip size smaller near 0 where the problem is. All the way through this analysis, we assumed h was constant, but there's no reason whatever why it needs to be. You can divide it into non-uniform strips, and in each one the h can be different. So whatever method you're using, whether it's trapezoid or Simpson or Gauss quadrature, you can use much smaller step sizes near the origin, and you'll get much better results.